Hi, so my name is Akshay Agrawal. I was at Google Brain from 2017 to 2018, and I'm now a PhD student in the convex optimization group here at Stanford. So I'm going to talk about TensorFlow Eager, and TensorFlow Eager is a part of TensorFlow that makes it possible to mix both imperative programming and declarative programming. So the emphasis in machine learning research has recently shifted from building static DNNs to differentiating through complicated programs. And these complicated programs might have data-dependent control flow, they might use complicated data structures, and so on. Because of this shift, libraries for machine learning or for differentiable programming are becoming more and more complicated, and it's come to the point that an argument has been made that these libraries are beginning to resemble domain-specific languages. And these so-called DSLs are usually embedded in a host language, and the language is usually, but it's not always, Python. Most of these Python libraries offer one of two different programming styles. So they're either imperative, like chainer or torch, where operations are executed immediately, or they're declarative, like TensorFlow or Theano, where programmers first construct data flow graphs before executing them. There are some exceptions to this dichotomy, like MXNet, JAX, and PyTorch 1.0, which do let you hybridize the two programming models. So imperative programming has many obvious advantages. I mean, the first and foremost, it's really easy to get started with it because it offers a familiar programming model. And it also sort of enables programmer creativity because you can use the full extent of the host language. The main drawback is that if your library is a Python-based library, then your performance can become bottlenecked on the interpreter when the operations you're running are very small. So there is a reason, of course, that TensorFlow was designed around data flow graphs. By separating the specification of your program from its execution, you're no longer bottlenecked on the interpreter, the Python interpreter. And so then you can do things like whole program analysis, you can do compiler optimizations, your runtime can exploit inter-op parallelism, it can automatically reuse buffers, and so on. And having graphs as in IR also simplifies deployment, distribution, code generation, and serialization. The main problem with graph-based libraries like TensorFlow is that they have steep learning curves, and because you're limited to using the constructs that the library provides, such as like in-graph control flow, it becomes sort of prohibitively difficult to express certain types of models. So ideally, we'd have an imperative DSL that would let you drop into sort of more performance graph execution when needed. So the solution that TensorFlow Eager proposes is to mix imperative programming and declarative programming or graphs in a way that can be interpreted as multi-stage programming. Multi-stage programming is a well-studied technique in programming languages, and it can be discussed in a very formal way, but we're going to keep the discussion at an extremely high level in this talk. I should say that TensorFlow Eager is not unique in offering this kind of programming model. Again, so MXNet, JAX, PyTorch 1.0, and more recently SNEC plus Autograph all offer sort of similar programming models, but we'll use TensorFlow Eager as the case study here. So by default, in TensorFlow Eager, all operations are executed imperatively or eagerly. For users that want any of the benefits that graphs provide, we provide a decorator at tf.function that will stage Python functions into graph functions. And it does this in a just-in-time way. A graph function is just a TensorFlow graph that has named inputs and outputs. TensorFlow Eager is implemented as an opt-in extension to TensorFlow today, and it's compatible with basically all of our TensorFlow APIs. In 2.0, TensorFlow Eager is always enabled. TensorFlow 2.0, that is. So this is a simple code example that shows what imperative execution looks like in TensorFlow Eager. The second line of code there essentially transforms TensorFlow into TensorFlow Eager, so it's important. And everything else is as you would expect. TF.1s returns a concrete tensor backed by numerical data, and the add operation will execute immediately. By adding that single line at tf.function, transforms the add function into a Python callable that will execute an equivalent data flow graph. And you can see that from the programmer's perspective, executing a graph function is syntactically equivalent to executing the corresponding Python function. And you can also see, if you look at the last line of code, that the graph function is polymorphic in the types of its inputs, even though TensorFlow graphs are not polymorphic. So we'll talk a little bit about how we do that in just a minute. And I guess another thing to notice is that there are no TensorFlow sessions in sight anywhere. That's because the decorator abstracts away both the graph construction and also the graph runtime. So at a very high level, this is the multi-stage workflow that we recommend to most users of TensorFlow Eager. The first step is to obviously implement your model or your differentiable program, but to implement it in sort of purely imperative mode, because that will let you use things like Python debuggers and so on. And the second step is if the performance of your program is not to your liking, then you drop in, you use whatever Python profiler you want, you use PDB to find bottlenecks. And then specifically, you find bottlenecks that consist of TensorFlow Eager code. And the third step is to refactor those bottlenecks into functions, Python functions, and then add tf.function decorators to stage them into graph functions so you can recover performance. We anticipate that most people won't need to do the second and third steps, especially if they're sticking to our high-level APIs, which are already performant. So I'll provide just a few details on how we've implemented imperative execution, very few. As a recap, in TensorFlow, primitive functions are called operations, and their implementations are called kernels. So basically, in TensorFlow Eager, we execute the exact same set of TensorFlow operations by instantiating the kernels right before they're needed and then executing them. One nice thing about this is that whether the operations are executed as part of a graph function or whether we execute them eagerly, we execute the same code. So this is conceptually simple. The details of sort of making all of our Python API functions safe to run eagerly that was another story, and it was actually a lot of work, but that's not the focus of this talk. When we transform imperative code to graph functions, we try as much as possible to preserve the semantics of the original Python functions. So many of the details that I will show you about graph functions are motivated by this desire. So as I've said, the tf.function decorator is a just-in-time tracer. The first time the Python function is run, the tf.function will execute the wrapped Python function in a graph construction context. And it will generate a graph function that consists of all the TensorFlow ops that were run during the trace. So it's important to note that tf.function is not a compiler for arbitrary Python functions. So specifically, if you have something like for I in range 1 million, that will turn into a TensorFlow graph with 1 million nodes potentially. The object that tf.function returns is polymorphic. And what I mean by that is that it specializes its traces on the d-types and the shapes of tensor inputs and the runtime values of the non-tensor arguments. So essentially when it's called, when a decorated function is called, we'll infer the input signature. And if the input signature doesn't match something that we've seen before, we'll trigger a new trace of the Python function. So that means that multiple concrete graph functions might be generated for a single Python function. And this type of runtime specialization is very similar to what's done in JAX, and it's also sort of conceptually similar to lightweight modular staging. And also to sort of to make it sort of seamless to insert tf.function into existing imperative code, we've made it so that you can lexically close over tensors and tf variables while using the tf function decorator. When TensorFlow variables are used in functions, we do a bit of extra work in order to ensure that the ordering of reads and writes to variables in graph functions matches the Python ordering in the original Python function. So Specifically, when tf.function generates graphs, it will automatically insert control dependencies that ensure two things. First, we'll ensure that all stateful operations are run, and that operations which modify, so the second thing is that we'll ensure is that operations that modify the same resource run in program order. And importantly, we try to do this in a way that we insert the minimal amount of control dependencies possible so that the function runtime can still exploit parallelism in the graph. So I said that tf.function was just a Python tracer. I lied a little bit in that we have actually recently added the ability to rewrite a subset of Python control flow to TensorFlow control flow. So specifically, Python control flow that depends upon tensor data will be rewritten to graph control flow. And this rewriting is done via autograph, which is the subject of the next talk, so make sure you stick around for that. So with respect to how functions are actually run, we instantiate them in per-device runtimes, and the runtime automatically will parallelize and optimize each function before running it. It's essentially very similar to the runtime for classic TensorFlow, for TensorFlow graphs. And functions themselves are executed by operations, just like any other primitive in TensorFlow. And because of this, we get as a consequence that functions are very easy to compose. For one function to call another, all the first function has to do is to have like a literal function call operation embedded inside of its graph. This also has a nice side effect of helping us limit the size of graphs when we are sort of, if you're stamping out multiple subgraphs, you can instead just have n calls to the same function. The fact that functions are executed by operations also means that it's easy to customize the runtime behavior of functions by writing your own special function call operations. So as an example of that, we use a special function call operation to execute functions across multiple devices. And this function call operation essentially replicates a subset of TensorFlow sessions inside the operation. So it reuses technology like the graph placer and partitioner, which will take a TensorFlow graph and partition it across a set of devices. And we even extended this op to create another special op whose device was configurable at runtime. So that let us retarget where the function was running at runtime, and this was useful for load balancing in production. Of course, TensorFlow Eager would not be a library for machine learning if we did not have automatic differentiation. We support a tracing-based reverse mode automatic differentiation. And in our programming model, we explicitly expose the trace, or as we call it, the tape, to our users so that they can limit the overhead incurred by tracing. And this is a simple code snippet that shows how tracing works, gradients work. So the tf.gradient tape is the main entry point into the gradient API. It's a context manager, and it can be nested in order to compute higher order derivatives. The watch method on tapes marks a tensor as something that we'll need to compute a gradient for or with respect to later. If you use variables, they would be watched automatically. And I should mention that the tape is tightly integrated with functions. So when a function is called under a tape, we'll do what's necessary. So we'll modify the forward pass to output and store intermediate values, and then we'll generate a function that will compute the backward pass. So the gradient tape actually recently acquired the ability to compute Jacobians. And this computation is automatically batched using a parallel for construct that was, I think, recently designed in the past couple of years. This is actually pretty new. This detail is not even in our paper. For the evaluation, I will show two experiments that compare the performance of TensorFlow Eager and graph-based TensorFlow. So this first one shows the examples per second achieved while training a ResNet 50 on ImageNet on a GPU. The y-axis is the examples per second. The x-axis is the batch size. And the red colors correspond to a purely imperative TensorFlow Eager implementation. The blue bars correspond to TensorFlow Eager with judicious use of the TF function decorator to basically turn the forward and backward passes into graphs. And the orange bar corresponds to pure TensorFlow. So you can see as when the batch size is small, there is a significant difference in examples per second. Functions help a little bit. But as the batch size increases, the difference between imperative eager and eager plus functions seems to vanish. And the difference between those two in TensorFlow also becomes much smaller. Where TensorFlow Eager does take a significant hit in performance is when we're running programs that have tons and tons of very small operations. And in this case, the Python overhead incurred while running these operations tends to dominate the actual amount of time spent computing the kernels. So this chart shows the examples per second achieved while training a MCMC method from the generalized Hamiltonian Monte Carlo method L2HMC paper. The y-axis is again examples per second, x-axis is number of samples. The colors are the same as before. So Eager is obviously like 2 or 3 orders of magnitude slower than graph TensorFlow. The promising, sort of the optimistic way to read this chart is to say that by using function judiciously, you will recover essentially all of your performance. But I think this involved basically using function to turn the vast amount of the code into a graph. Okay, one more thing. The data is from September of 2018, so perhaps numbers have improved. Some future work. A lot of it has to do with performance optimization that's easier for graphs than it is for eager execution. So we still have plans to develop a way to execute eagerly, but also asynchronously. We have a prototype, but that prototype is far from done. It's not clear how to reuse memory buffers for temporaries in Python, whereas we do, again, have some type of solution for that for graphs. And also, we're working on getting SPMD working efficiently across multiple devices. And the last thing that we want to do is make it possible to stage more and more code as graphs. And one key thing that this will involve is representing more interesting data structures in the graph. And autograph, again, will probably be quite useful in this task. And that's all I have. Thank you.
Heidi, UIUC, great talk. I have one question about multi-device support. So in TensorFlow, when there are part of the graph running on the different devices, TensorFlow automatically adds send and receive ops. If this happens inside a function, how your GIT deal with it?
Yeah, so that's a great question. Actually, so we do the exact same thing. So if your function has TF.device annotations, and when we're running the function, the first time the function is run, it'll be we'll partition it and automatically add the sends and receives.
Great, thank you.
Yeah.
Any more questions?
Yes. Simeon Wei from CMU. This great talk. My question is, are there things that programmers can do with TensorFlow but cannot do with the TensorFlow Eager?
I don't think so, because essentially, like, if you just write your entire program as one function that has tf.function on top, then essentially you can replicate all of what you can do in TensorFlow because you have a graph.
Okay. Okay, thank you.
You're welcome.
Do we have any more questions? All right, let's thank Akshay again.